So here we have a matrix A that we are going to consider the corresponding linear system for dy dt equals ay. And let's solve the system a couple ways. Let's use the books method, and then let's use diagonalization. So what's going to happen here with the books method, and in both methods, in fact, we need to think about the characteristic polynomial, which now we're used to writing it as lambda squared minus the trace times lambda plus the determinant. The trace is -5, right? Some of the numbers in the main diagonal, -4 plus -1 is -5, but we're subtracting the trace times lambda, so that becomes +5 lambda. And the determinant is 4 minus 4, 0. That's strange. Yes, that happened. We got a 0 determinant here. First thing that you should think of when you get a 0 determinant for your matrix A is that it's not invertible. And that also means for the system, because it's not invertible, it's going to have a non-trivial kernel. There are going to be infinitely many equilibrium points. What? Yes. Infinitely many equilibrium points to the system. We've never really encountered that before for the linear systems. Where are they? Well, we could think about no-clines, but let's keep going with this. This can be factored as lambda times lambda plus 5. Set that equal to 0. Evidently, we do have two eigenvalues that are -5 and 0. But wait a minute, I thought 0 can't be an eigenvalue. No, 0 can be an eigenvalue. The 0 vector cannot be an eigenvector. But the number 0 can be an eigenvalue, and it is the case here. What's the eigenvector for lambda equals -5? Take the first row here, -4 minus -5 would be +1. Maybe you want to confirm we definitely have a system with more than one solution by also considering the second equation, 2x, -1 minus -5 would be positive, -1 minus -5 would be +4. Yeah, these are scalar multiples of each other. There are non-trivial solutions. We could solve for x in terms of y and think of y as a free variable and write an eigenvector. Take the y to be 1 and then x would be -2. And for lambda equals 0, what would the system be? Yeah, these rows are already multiples of each other, aren't they? They're already scalar multiples of each other. They had to be. The determinant was 0 for a 2 by 2. If I'm subtracting 0, I really just get the original coefficients. Solve for y in terms of x, say y equals 2x, and your eigenvector, taking x to be a free variable and equal to 1, is 1, 2. Interesting thing to note here, these vectors are perpendicular, aren't they? Look at their dot product. -2 times 1 is -2. 1 times 2 is +2. -2 plus 2 is 0. These vectors are perpendicular or orthogonal to each other. That's going to be relevant for our diagonalization. But we're not doing diagonalization right now. What does this mean about the general solution? K1 e to the -5t times -2, 1. That looks similar to what's usual. Plus K2 e to the 0t, really? Times 1, 2. Yes, it is e to the 0t, and yes, that is equal to 1 no matter what t is. It's okay. It's just happening. It's just what happens in this example. That doesn't stop us from writing the general solution, though. It just looks different than usual. And then we can use this to solve initial value problems. But let's just think about it for the moment. What would happen if K1 is 0? What if we solve an initial value problem and get K1 equal to 0? Then this term would go away, and you'd be left with a constant vector. Doesn't depend on t. I guess that's got to be an equilibrium point. It's not moving, not changing over time. So if K1 is 0, our solution is constant. All equilibrium points lie on the line to the origin parallel to that vector 1, 2. Parallel to the vector 1, 2, about like this. This is a line of equilibrium points, infinitely many equilibrium points. Every point on that line is an equilibrium point. I guess other solutions where K1 is non-zero decay to 0 in this component at least, but not there. I guess there is if K2 is 0, this is a straight line solution heading toward the origin as t increases, parallel to -2, 1, which is going to be perpendicular to this vector, this line here. There is a straight line solution heading to the origin like that. But all other solutions actually are straight line solutions as well. They head to non-zero vectors. This is a pretty strange looking phase plane, isn't it? But that's the way it is. A rare phase plane, you could call it degenerate or singular. This is the kind of phase plane you get sometimes with transitions between different types of behaviors, bifurcations. In the trace determinant plane, you get infinitely many equilibrium points when d is 0, when you're on the trace axis. Talking about a bifurcation problem, which is this is not, but if it were a bifurcation problem, you cross the t-axis where d is 0, that's going to be a value where your system is going to have infinitely many equilibrium points. So this is a transitionary kind of system between different kinds of behavior. But there's something else that's important here for us in mixing differential equations with linear algebra. We want to talk about diagonalizing this matrix as well, and then matrix exponential. So what have we done with diagonalization so far? We've found the eigenvalues, found the eigenvectors. I guess I can put these vectors in a matrix P, and that would be my change of coordinates matrix, and that would be fine. But it's not the only way to diagonalize in this case. And you might say it's not the best way to diagonalize, especially when this kind of system gets generalized to bigger systems like 3x3 or 4x4 or 5x5, heaven forbid. It turns out to be not best to use these vectors as they are, but to normalize them. Find a unit vector in the same direction by dividing them by their lengths. That turns out to be a better method because what will happen is your P matrix will be what's called an orthogonal matrix, and that's really good because it means its inverse will be its transpose, amazingly. And while in general inverses are very computationally expensive, transposes are not very computationally expensive. Your matrix could be 100 by 100. It's easy to find the transpose. Inverse, not so much. You put a 100 by 100 matrix into a computer and say, find the inverse, it's going to take till eternity. Probably millions or billions of years, even a very fast computer. Okay, so you don't want to, it's nice when you can just take the transpose, which it turns out you can. Not only does this matrix have 0 as an eigenvalue, so it's special in that way, but it's also what's called a symmetric matrix. Its transpose equals itself. Really? Yeah. Take the first row, make it the first column, you'll get the same first column. Take the second row, make it the second column, you'll get the same second column. This is happening because these two numbers are the same. It's symmetric about the main diagonal, you might say. There's symmetry here. Reflectional symmetry, yeah, kind of. As if the main diagonal is a mirror. The key thing is the transpose equals the matrix itself. Symmetric matrices are very special. You might say they're rare, but they're an important kind of rare. They never have complex eigenvalues. It's always real eigenvalues. That's a fact to know about symmetric matrices. They always have real eigenvalues. And they are always orthogonally diagonalizable. If I take these vectors and normalize them, divide them by their lengths, which they both have the same length actually, square root of 1 squared plus 2 squared, square root of 5 is the length of each of those. Oh, really? I'm going to get non-perfect square roots. Make a matrix P whose columns are the same columns as before, but divided by the length. This doesn't seem like it's very good. If I do this, though, something nice happens. It becomes what's called an orthogonal matrix, and its inverse equals its transpose. And its transpose in this example happens to equal itself. It's symmetric. That won't always happen here. I mean, in fact, if I put the negative sign down there, it wouldn't have happened. This matrix is its own inverse. Weird, but true. You can check it. Multiply this matrix times itself. Negative 2 over root 5 times negative 2 over root 5 is positive 4/5. 1 over root 5 times itself is 1/5. 4/5 plus 1/5 is 1. This times this is negative 2 over root 5. This times this is positive 2 over root 5. Add those, get 0. Negative 2 over root 5 plus 2 over root 5 is 0. 1 over root 5 times itself is 1/5. This times this is 4/5. 1/5 plus 4/5 is 1. This matrix is its own inverse. Again, that didn't have to happen. And in fact, again, it wouldn't have happened if I put the negative sign in this first column down there, which I could have done. But the transpose still would have been the inverse, and the transpose is still easy to compute. So it's not such a big deal with 2x2 systems, you might say, because finding inverse matrices of 2x2 matrices is not that hard. But generalizing these ideas to bigger matrices definitely pays off. And then if we did diagonalize, if we computed P inverse AP, we would get a diagonal matrix with the eigenvalues in the main diagonal, -5 and 0, really? This matrix, D, would have mostly zeros in it. It is a diagonal matrix because the things off the main diagonal are all zeros. Yes, this number on the main diagonal is also a 0. That's okay, it's still a diagonal matrix. And its matrix exponential is easy to compute. Careful, e to the 0 would be 1. And then it would be easy to compute. Maybe easy is the wrong word, but relatively easy to compute solutions of initial value problems like this with the matrix exponential. I won't actually do the calculation. And as always, this corresponds to change of coordinates. Y equals PU, equivalent to U equals P inverse Y. And ultimately, the system in U coordinates would be DU And that'll be a completely decoupled system in general when D is diagonal. And then in this case, it's really simple. And the coordinate changes, the skewed coordinates do correspond geometrically to the eigenvector directions along that line and this line.